Theorem 1. Theorem 1. It is a generalization of Nader type vanishing theorem. Nader type vanishing theorem. Okay. Let X be a normal projective variety. Normal projective variety. Of course, everything is defined over C. This talk. Normal projective variety, and B is a boundary Q divisor. Q divisor on X. Boundary means the questions of B is between 0 and 1, and we assume XB is log canonical. And D is a Cartier divisor on X, such that assume D minus Kx plus B is ample. And let this Ci be any set of log canonical centers, LC centers of this pair XB. Okay. We put W equal union Ci, okay, with reduced scheme structure. Okay. In this case, higher cohomology HI X IW tensor OXD equals 0 for any positive I. IW is defining ideal C, ideal C of W. Okay, and in particular HI XOXD equals 0 for any positive I. Okay. In particular, the restriction map H0 OXD to H0 W OWD is surjective. So this is powerful result. We can extend a section on W to the whole space. Okay. The remark: if W is if Ci is a set of all LC centers, then IW equal IXB multiply ideal C prior ideal C. So in this case, this vanishing theorem is Nader vanishing theorem. The key point is that Ci is any set of log canonical center. Okay. I will prove this theorem in detail. Let f y to x is a resolution such that support F. This is a strict transform B union exceptional locus of F is a simple normal crossing divisor. We can take such a resolution by Hironaka, and we assume F inverse W, the set theoretical inverse of W is also simple normal crossing divisor on Y. Yeah. And we can write Ky, this is a canonical divisor of Y plus By equal F fullback Kx plus B. More precisely, By is defined by this equality. And let T is a union of the irreducible components of By equal 1. I explain this notation later. That are mapped into W by F. Okay, remark, if By is summation Bi, then By equal 1 equal summation Bi, this sigma runs through By equal 1, and B1 less than 1 equals summation Bi. Yeah, Bi is less than 1. Okay. I use this notation throughout this
assumption By is less than 1.
Sorry?
By
Yeah.
is less than or equal to 1.
Less than or equal to, yeah. But By is, in general, By is not effective, so it is an important remark. Okay. We consider the following short exact sequence: Oy A minus T, Oy A to OTA, where A equal minus round down of By less than 1. Okay. By the definition of this divisor, A is effective. Okay, A is effective. The coefficient of By less than 1 is less than 1, and round down of this divisor is a negative divisor. So A is effective, and it can be easily checked that A is F exceptional. Since B is an effective divisor, so A is F exceptional. So we obtain F push forward Oya minus T to F push forward Oya. This is nothing but Ox, and we obtain this exact sequence. This is a connecting homomorphism. Okay. Okay. In general, it is not 0. So, yeah. In general, this CIF is not 0. However, since A minus T is here, A minus T minus Ky plus By fractional part. This is By minus By round down, the fractional part of By. plus by equal 1 minus t is equal to minus ky plus by. This is obviously equality by the definition of A, and t is cancelled by this t, and A is this one, and so this is obvious equality. So this is Q linearly equivalent to f pullback minus f pullback kx plus y, kx plus b. Okay. So by theorem E1, any non-zero section any non-zero section of this C or y a minus t contains in its support the F image of some strata of y by fractional part of by plus by equal 1 minus t. Okay. On the other hand, ft equal w by the definition of t. By the definition of t. Okay. Therefore, delta is a zero map. Okay. In general, this CF is not zero, but the support of this CF is contained in Ft. Ft is W by definition, and the associated prime of this CF is the generic point of the F image of some strata of this pair, and by definition of T, there are no associated prime inside W. Okay, so in general, this CF is not zero, but connecting homomorphism is zero. Okay, therefore, we obtain 0f push forward Oy a minus t to Ox to f push forward Ota to 0. Okay, so we obtain Ow is isomorphic to Ota, and it is obvious that Iw is isomorphic to f pullback Oy a minus t. Okay. So we obtain lemma 2. Lemma 2, f push forward Ot is isomorphic to Ow because A restricted to T is effective. Okay, effective. So this follows from this isomorphism. Okay. And since f pullback d plus a minus t minus ky plus fractional part of by plus by equal h minus 1 minus t is q linearly equivalent to f pullback d minus kx plus b. Like this. Okay, and this is ample by assumption, and f pullback d plus a minus ky plus fractional part of by plus by1 is q linearly equivalent to f pullback d minus kx plus b. This is also ample. Okay. Then this part is theorem E2, vanishing part of theorem E. Then HI X IW tensor OXD equal HI X. This is this one. So F push forward OY A minus T tensor OXT. Okay. So this is equal. This is 0 by theorem E2. Okay. D plus A, F pullback. This is F push forward OY F pullback D plus A minus T. And F pullback D plus A minus T minus something is pullback of ample divisor. So we can apply theorem E2. So this is this cohomology is 0 for any positive I. Okay. Okay, next, HI XOXD is isomorphic to HI X F push forward OY A tensor OXD. By the same argument, it is 0 for any positive I. Okay, by theorem E2. Okay. By the long exact sequence, like HI XOXD, HI W OWD, H I plus 1, X IW tensor OXD. By using this long exact sequence, we obtain this. Oh, yeah. We obtain this is this surjection and so by this long exact sequence, the restriction map is surjective and HI W OWD equals 0 for positive I. Okay, both sides are 0, so middle part is 0 for any positive I. Okay. Okay. Yeah. This vanishing theorem is very powerful in the study of log canonical pairs. I need 2 more theorems for applications. 2 more results for applications. As a corollary of lemma 2, we obtain corollary 2. That's a lemma 2. This one. Corollary 3. Let X be a log canonical pair, LC pair. Then the following statement holds: an intersection of 2 LC centers is a union of LC centers. The second one, any union union of LC centers of this pair XB is semi-normal. Okay, and the third one, most important one, let x be a closed point. Small x is a closed point, such that xb is log canonical, but not KLT at x. So some LC center passing through x. Then there exists a unique minimal. Minimal means minimal with respect to inclusion. Minimal LC center Wx, W sub small x, passing through small x, and Wx is normal at x. Okay. We can check these properties without any difficulties by using lemma 2. Lemma 2 implies that W is the target space of a simple normal crossing divisor with connected fiber. Okay, so we can easily check part 1, and part 2 is obvious since T is a simple normal crossing variety, so T is semi-normal, and by this relation, W is automatically semi-normal. And part 3, by using each one, it is obvious that there exists a unique minimal LC center passing through Wx, and Wx is minimal, so by shrinking x around small x, every strata of T dominates Wx. So Wx it is easy to check Wx is normal at x. Okay, final theorem. The next theorem is much more difficult than theorem 1 and this corollary, but very useful for application. Okay, theorem 4. This theorem is very non-trivial. XB is a projective log canonical pair. This means this pair is log canonical and X is a projective variety, and W is a minimal LC center of XB. Okay, minimal with respect to inclusion. Okay, and D is a Cartier divisor on W, not on X. D is a Cartier divisor on W, such that D minus Kx plus B restricted to W is ample, of course, on W. Then the higher direct image HIW OWD equals 0 for any positive I. Okay? This theorem is much more. This one?
Ax plus B could be Q Cartier.
Yeah, Q Cartier.
So Q Cartier is Q Cartier.
Yes. So M times Kx plus B is so there is a line band restricted W and formally taking minus. Okay.
Yes, yes, yes.
Okay. This is just Q-Kalte divisor. Okay. There are two different proofs. Proofs. First one, we can generalize theorem E for a simple normal crossing variety Y. In theorem E, Y is assumed to be smooth projective variety, but we can generalize theorem E for projective simple normal crossing variety Y. It is very technical part. It is very technical, but we can generalize theorem E for simple normal crossing variety. Then theorem 4 OK. This theorem is purely Hodge theoretic. Not pure Hodge structure, purely Hodge theoretic proof. But not so easy. It's technical. Okay. Second proof, by using BCHM, Bilka, Cassini, Heikon, McCarnan, a great paper of the log minimal model program for KLT pairs. By using BCHM, we can reduce theorem 4 to theorem 1. Okay. This proof is easy. Modulo BCHM. Okay. 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 Yeah. I make one important remark. Theorem 1, corollary 3, and theorem 4 were already well known, and under the assumption that there exists an effective divisor B prime such that X B prime is chaotic. Okay. Under this assumption, by using perturbation technique, theorem 1 follows from the usual Nadel vanishing theorem, and corollary 3 is a result of Kawamata about 10 years ago. And the theorem 4 can be proved by using Nadel's vanishing theorem and Kawamata's subadjunction. But we need this artificial assumption. And this assumption does not necessarily hold in general situation. So, okay, let's go to applications of theorem 1, corollary 3, and theorem 4. Okay. Well, by using new techniques, some results can be proved without using any difficulty. Okay, theorem 5. This is non-vanishing theorem. Theorem for log canonical pair. pairs. XB is a projective log canonical pair, LC pair. This means X is a projective variety and this pair is log canonical, and L is a Neff-Cartier divisor on X, such that A times L minus Kx plus B is ample for some positive A, positive integer A. Then the base locus of the base locus BSML of the complete linear system ML contains no LC centers of pair XB for any M greater than or equal to some fixed M0. Okay. Okay, remark. Our first remark is if XB is chaotic, chaotic means there are no LC centers. So if XB is chaotic, then theorem 5 claims nothing. Okay. And the second remark, theorem 5 is correct. I think theorem 5 is a correct generalization. Correct generalization of Professor Shokrov's non-vanishing theorem. This theorem greatly simplifies of the proof of fundamental theorem of log minimal model program, or base point free theorem, cone theorem for log canonical pairs. Yeah. Once we obtain theorem 5, non-vanishing theorem, then the next theorem is almost obvious. Base point free theorem. Theorem for log canonical pairs. Same assumption as in theorem 5. So this means XB is a projective log canonical pair and L is a Neff divisor, such that L minus Kx plus B is ample. Then this complete linear system ML is base point free for any M greater than or equal to some fixed M1. Okay? So obviously theorem 6 is much better than theorem 5. But I think it is not. I think theorem 5 is much easier to treat. So first I prove theorem 5, and as a corollary we obtain theorem 6. I think this formulation is very useful. Almost all applications, the base locus of some complete linear system contains LC center, then some trouble happens. So this formulation is very useful.
I'm sorry, in your definition of log canonical center, I mean, this happened earlier. Do you consider the generic point of X to be a log canonical center of X?
No.
So that's not saying anything about the non-vanishing.
Yes. So XB is chaotic. So this statement, this theorem claims nothing.
But in fact, then the next theorem you say you get it anyway.
Sorry? So I will explain how to prove theorem 6 by using theorem Go later. Okay. From now on, I explain the proof of theorem 5 in detail. In my proof of theorem 5, we do not need Hironaka's resolution, perturbation technique, perturbation of questions, and so our proof is much simpler than Kawamata's X method. I think my proof is much simpler than Kawamata's original X method, and my result is much better than his result because XB is log canonical. Kawamata's X method can only apply for KLT pairs, but our method can be applied for log canonical pairs. Okay. Proof of theorem 5. Okay. W is a minimal LC center of pair XB. Okay. Step 1. If L restricted W is numerically trivial. This means numerically trivial. Of course, L restricted W is NEF because L is NEF. Okay, restriction to NEF cavity divisor is NEF. So in this step, we assume restriction of L to W is numerically trivial. Then H0 OWL equal chi W OWL by theorem 1. Okay? L minus kx plus b is ample. So by using theorem 1, were result explained in the proof of theorem 1. This is a higher cohomology of this vanishes. So we obtain this equality, and L restricted W is numerically trivial. So this is nothing but chi WOW, and this is H0 WOW, theorem 4. Okay. On W minus kx plus b restricted W is ample. So we can apply theorem 4, and this is 1. Okay. So in this case, L restricted W is numerically trivial. Okay. We just assume linearly trivial. Okay, so ML restricted W is base point free for any M. It is obvious. On the other hand, the restriction map XOX ML to H0 W or WML is surjective for any M. M is greater than or equal to A. Okay. A is this A. Okay. By theorem 1. So the base locus of ML does not contain W for any M greater than or equal to A. Okay? So So the restriction of L to W is numerically trivial, then W is not contained in the base locus of this linear system for any m. M is greater than or equal to A. This step is key step. Okay, step 2. In this case, L restricted to W is not numerically trivial. Okay? Let small x is a general point. General point of this minimal LC center. And L is sufficiently large, large integer. Then we can find n. N is linearly equivalent to b times L minus kx plus b restricted to W with multiplicity x. Multiplicity of n at x is larger than b times dimension W. This part is well known as Professor Shokrov's concentration method. Yeah, now this part is well known and classical technique. By using the estimate of the leading term of Riemann-Roch theorem, we can find such divisor n on W. N is a divisor on W. Okay. Okay, and if in this case, if B is sufficiently large, then defining ideal sheaf of W tensor OX B L minus KX plus B is generated by global sections. Okay, this divisor is ample, so taking B sufficiently large, then any coherent sheaf tensor, this sheaf is generated by global section. So we take sufficiently large B. And this one, HIX IW tensor OX B L minus KX plus B equals 0 because this is ample. Ample and B is sufficiently large. This cohomology is 0 by Sells vanishing theorem. Thus, we can find the Q divisor M, effective Q divisor M on X, such that part 1 M restricted to W is effective Q divisor such that multiplicity of M restricted to W to at X is greater than dimension W. And the second one, M is Q linearly equivalent to LL minus KX plus B. And the third one, XB plus M is log canonical outside W. Okay, I think it's an easy exercise. So N is divisor on W. So by taking some multiple and using this vanishing and this result, we can we can extend some multiple n over the whole space X, and by dividing some constant, we obtain effective Q divisor M. Restriction of W is N over B. Okay, so this condition is obvious. Okay, M restricted to W is N over B. So by this condition, we obtain first condition. By the construction, some multiple of M is the extension of some multiple of N. So second condition is also obvious. And by using this condition, by taking general extension, this pair is log canonical outside W. Okay, outside W, we can choose general extension. Yeah, this technique is also well known. For example, in the proof of Angelon-Schur's effective freeness result. Yeah. Okay. We put C is a log canonical threshold. So log canonical threshold means T is a real number and X B plus Tn is log canonical. It is well known as log canonical threshold. Then X B plus Cm is log canonical. Of course, not KLT. And C is between 0 and 1. Okay? Okay, this part is important. This follows from this estimate.
Max is a soup.
Yeah. Max is soup, but attains some rational number in this case. Yeah. So by this condition, M is very singular at X. So log canonical threshold must be less than 1. Okay. And by the construction of M, M does not contain any log canonical center of Kx plus B, so C is positive by the construction. It's very important and usual technique in the non-vanishing theorem. And this new pair XB plus Cm has a log canonical center W prime, which is strictly contained W. Okay, by using corollary 3. Any intersection of log canonical center is a union of log canonical center in corollary 3. So by the construction, this pair has a new LC center passing through X, and so there exists a strictly smaller log canonical center inside W. Okay, since A minus AC plus CL minus Kx plus B plus Cm is Q linearly equivalent to 1 minus C AL minus Kx plus B. This is ample because C is less than 1. Okay, so we can replace XB with XB plus Cm and A with A minus AC plus CL. By repeating this process, we reach a situation L restricted W is numerically trivial. This is step 1. Okay, one. So we obtain theorem 5. Okay. If L restricted to W is numerically trivial, then theorem 5 is obvious by this argument. If L restricted W is not numerically trivial, then by using this method, we can cut down the minimal logical center, and W prime is smaller dimension than W. So we reach the situation of this. Okay. So apply the argument in step 1, we obtain theorem 5. In this proof, we do not Hironaka's resolution nor perturbation of questions. Yeah, much simpler than Kawamata's original base point free theorem technique. I think theorem 6 is a good exercise once we obtain theorem 5. I explain it. Proof of theorem 6. Okay. Step 1. If L is numerically trivial, then H0 XOX plus minus L equal chi X OX plus minus L by theorem 1. Vanishing theorem. Okay? And this is equal to chi XOX. Okay? It is because L is numerically trivial, and this is equal to H0 XOX. This is again theorem 1, and this is 1. So L is linearly trivial. So in this case, ML is free for any M. So from now on, we can assume that L is not numerically trivial. So step 2, in this case, if assume XB is KLT, okay? So this means there are no LC center. In this case, we can find M. M is Q linearly equivalent to LL. So from now on, we can assume L is not numerically trivial. Okay? In this case, we can find such a divisor with multiplicity xm is larger than dimension x. X is a general point of x. Completely the same argument as in this in step 2. Shokrov's continental relation method, we can find Q divisor M, Q linearly equivalent to this divisor with very high multiplicity at general point X. By the Seeger arguments, we can assume that this pair is log canonical, not KLT. Okay, by replacing B plus log canonical threshold C times M, by replacing A with A minus AC plus CL, so we can assume XB is log canonical. So step 3. So in this case, XB is not log canonical, not KLT, and L is not numerically trivial. In this case, by theorem 5, we can take general members d1 dot dn plus 1 n plus 1 kl for some positive k and n equal dimension x. And we put d equal summation di, I equal 1 plus n plus 1. Okay, then xb plus d is not log canonical. Log canonical is log canonical outside the base locus of KL. It is because we take general member. So it is log canonical outside the base locus of this one, and not log canonical at the generic point of any log canonical center of XP. Since we take dimension plus 1 component. Okay, so C equal log canonical threshold x b plus c d is log canonical, and then C is C is between 0 and 1. It is because the base locus of this linear system does not contain any log canonical center, so C is greater than 0, and C is less than 1 because we take dimension plus one element. So by this, okay? And x plus b plus cd is log canonical, and x b plus cd has a log canonical center C such that C is contained in here. Okay.
X b plus d is not log canonical with the generic point.
This is non-empty, so this x plus b is not log canonical.
Some of the DIs has one point of multiplicity at least n plus 1. That's where you use C as somewhere.
Yeah. Apply theorem 5 again. Again, we can find k prime such that ds k prime kl is strictly less than contained ds kl. By the Noetherian induction, we obtain ML is free for some positive integer m. Okay. So by using theorem 5 to this new pair, we can find some large k prime such that k prime k base locus of k prime kl does not contain C. Okay, by the Noetherian induction, we can find M such that ML is free. So theorem 6 is okay. And by the same technique, rationality theorem, rationality and its consequence Kohn theorem can be proved for log canonical pairs. For the proof of rationality theorem, theorem 1 is sufficient. Okay? Rationality theorem for Kelt pair was proved by using Kawamata-Fiebeck vanishing theorem and Hironaka's resolution and Shokrov's non-vanishing theorem. But in our method, rationality theorem for log canonical pair can be proved only using theorem 1. we do not need Hironaka's resolution, perturbation of questions. We do not need Shokrov's non-vanishing theorem for KLT pairs. So I think my proof of rationality theorem for log chemical pair is much simpler than the traditional proof for KLT pairs. And the result is much stronger. Yeah. Okay.
You used resolution earlier.
Yeah. I used Hironaka's resolution in the proof of vanishing theorems. But once we obtain, we prepare correct formulation of vanishing theorems, we do not need Hironaka's resolution in the proof of these base point free rationality and non-vanishing theorem. Okay, I stop here.